All right, well, thank you very much, Alex. It is great to be back, as you mentioned. So my talk today is about making deep learning more robust, modular, and efficient. I should really say, credit the students here. The students my students are in bold, as well as my other collaborators on this work, without whom, of course, none of this would be possible. So as a brief overview, I think Patrick Winston from here always says you should begin each talk with a promise of what you're going to get out of this talk. One of the great sort of speakers and teachers of speaking, as well as, of course, in artificial intelligence. And so I'm going to start off with a promise, and we'll see if I deliver it by the end. And in this talk, I'm going to talk about, first of all, why deep learning systems are currently broken, which is surprisingly actually non-controversial in academic settings. You would think more people would put up objections, but everyone kind of agrees with that, surprisingly. But then I'm going to talk about how we at least begin to solve some of these things, at least in a limited sense, in some of the work that I and my students have done in these areas. And in particular, I'm going to talk about two main focuses, which is work on making provably robust deep models, counteracting a lot of the brittleness in deep learning. And then secondly, incorporating more structure in the loop as complex layers of these systems, which deals a lot with the opacity and the inefficiency of deep modeling. OK, so having said that, let me start this talk then by talking about what's wrong with deep learning. As I said, surprisingly non-controversial. But before I get into sort of start throwing cold water too much on this topic, I want to pause, because the reality is, as much as we'd like to sort of point out flaws as academics in deep learning, it's also worth taking a moment just to appreciate what's happened in this field and the, frankly, incredible things that are happening in this field. So I want to actually highlight 3 things from the past 4 months, which when you think about it, seems like an eternity in deep learning, that really sort of surprised me when I first saw them. And this is just amazing, these things, frankly. So I assume people have seen these things. This is not from our group. This is from general research community. The first is this StyleGAN paper, generating faces. So those are not real faces. It's a GAN generating fake faces. When I first saw that post on Twitter, I assumed it was a joke. Someone took an actual faces and said, oh, look how good GANs are these days. But no, those are actual faces generated by a generative model. They look amazingly realistic, especially probably at that resolution there. There was, of course, the GPT-2 language model that OpenAI released a few months ago, to much sort of hype and arguments about the hype. But when it comes down to it, this is also amazing at just sort of showing how good current language models are, right? So we can take like this preview of text here saying scientists discovered a herd of unicorns, and it makes up a very believable story about what's happened to these unicorns and about the nature and the name of these unicorns and things like this. Very, very believable in some sense, right, about what someone would write. So this just sort of shows how good we've come with language modeling. And then there's been the AlphaStar work that DeepMind has done. Again, I remember when DeepMind had their AlphaGo game, which I think, frankly, is a much more compelling, much more breakthrough event. But people sort of said, oh, that stuff works great because it's a fully observable game. It'll never extend to these cases of partial observability, long-term planning like this. It's just not in the cards. And 2 years later, we're all of a sudden playing these games that people thought were and maybe not solving them yet, but playing them well, games people thought were very far afield. So this is incredible, right, is the reality. And I don't want to degrade it all from this is just 4 months of work. These things have happened and really advanced the field. So this is amazing. But now, of course, let me throw that cold water on it that I promised you was coming. Because what I will say about these domains is that the stakes are all pretty low in them, right? If you generate a bad face, probably not the end of the world, right? If you make some text that you start off with some text and the story doesn't make sense afterwards, again, probably not the worst thing in the world if you predict the next word wrong in a language model, or if you don't play, if you lose one game in StarCraft, it's not that big a deal. You can kind of recover from that as a society. We can recover from that. The challenge, of course, comes when we talk about now going from this to things like autonomous cars, where errors can have disastrous consequences, or automated health decisions, where these stakes really are much higher here. All right, and when we transition from the realm of simulation, the pure virtual, to the real world, I do believe that the challenges and problems that we're sort of I'm gonna bring up here become much more pressing, and we need a much greater degree of assurance about our deep learning methods. So I want to point out 3 problems that I think are crucial to modern deep learning, and I'm going to talk about how we can begin to address these things. Yes?
The examples in the previous slide were all generation, and these ones are classification.
So I wouldn't call self-driving cars like classification. I would call it, it's a control, it's an equally difficult problem. It's control, it's everything. So I think it's more that they're simulation, whereas these are the real world. And you can't mess up in the real world even once, or you face big consequences. So the first problem I want to bring up is the brittleness of modern machine learning systems. So I assume most people have seen this figure here. Actually, by show of hands, who's seen this figure before here? OK, everyone. Good. Idea is you take an image perfectly recognized by a classifier, add a little bit of noise, adversarially chosen noise, by the way, and it classifies it very confidently as something else entirely. Now, I think this could be viewed as kind of an effect of this virtual domain, but it turns out actually, including with some work here at MIT, people have extended this to the real world. So you actually can actually manufacture objects. So this turtle on the right was worked here done at MIT. This turtle here is detected always as a rifle by image classifiers from any angle and rotation. There was some work by one of my colleagues at CMU on putting on glasses to make a face detection system think he's someone else. And there was some work out of Berkeley on putting stickers on stop signs to make it think it's a speed limit sign. And actually to this, I want to add one more to this that we've just published, actually. These are all sort of attacks on the object itself. So you're modifying the object. We just did some work to show that you can actually put a little bit of translucent film over a camera to fool things in a similar manner. So this is a camera that we put on top of a, let me turn that off. I don't know why, I don't really like this. OK, let me talk over it rather than have this great music. So this is a camera that this is a ResNet model looking at a stop sign, and it's correct, and it says it's the street sign class here, but it's correctly classified as street sign most of the time. We put a little bit of transparent, well-placed dots on a sticker in front of that camera. And the method looks, the image, it looks blurry. You can actually see them if you compare them side by side, but you wouldn't really notice that on the camera if you're just looking at it. And it can reliably call that stop sign a guitar pick from a variety of angles and positions with a single, of course, perturbation applied to every single image, which is restricted to be very blurry and sort of low frequency. So these things are not just hypothetical. They really do apply, and so it's being called a guitar pick most of the time there. They really do translate to the real world. I think these things are interesting as a potential security threat. So maybe people could actually attack systems. But some other work here actually also showed this is not necessarily even necessary for these things to be adversarial. Even incidental things like translations and rotations can also horribly fool classifiers. And I think this is actually opening up a fundamental question about the nature of decision boundaries that are learned by these things. The next problem I want to bring up is that of opacity. So these models that we have here, this is a ResNet 34 model. And if you want to ask a question like, well, what's this layer doing here? It's essentially impossible to answer that, right? We don't understand what the role of the different individual components of this network is. Now, I don't really care about that from a standpoint of maybe explaining in some abstract sense. But I do care about the fact that if the model isn't working, it's really hard for me to know what to do. So these things are very hard to debug, and it's hard to know, well, how do I change something to fix the performance of the system when these models have no sort of, there's no ends or goals for any particular portion of the network. And then finally, the last problem I want to highlight is the inefficiency of learning. So we all know that deep learning has solved games like Atari, right? This is sort of a famous result now 5 years old, maybe actually a little bit longer, 2013, or at least I shouldn't say solved. It has exceeded human performance in a whole lot of Atari games. But it takes a huge amount of time to actually achieve this. So a very simple game like Breakout, which is really simple to play, humans can pick it up very, very quickly. In a matter of minutes, we can play this game reasonably well. Deep learning, deep Q networks play it much better, but it takes them about 10 million images before they get to that point. It's about 6 days of continuous playing before they can really understand this one game here. right? And if you look at actually in context of sort of what most deep learning systems need in terms of their compute and data requirements, actually this is a pretty small one. So this is here is a chart that the OpenAI put together about the increasing computational demands of learning. And deep Q learning is actually way down here. It's actually the lowest example of needs for compute and data when it comes to deep learning. And so this is a large problem. If we talk about learning in real-world situations, we're not going to be able to run millions and millions of real-world situations. We're not going to be able to run millions and millions of simulations in order to before we get something right. And this is a final aside, and this is actually somewhat of an aside to the rest of my talk. But by the way, we don't really know why they work either. The theory here lags well beyond the practice of deep networks. The old theory would say things like, oh, well, the VC dimension of these things is the generalization error decreases something like the VC dimension over the number of square root of the number of samples. And this doesn't explain it because in deep networks we have many more parameters and samples, so you can't really explain it with these bounds. Now, fortunately, there has been some advances in this, some sort of new theory, which instead sort of omits the VC dimension and replaces it with a bunch of terms that sort of depend on the weights of the matrices and things like this in the network. But so there's no dependence on the parameters. That's good. But what we've actually showed in some recent work is that there's a minor problem here, which is that these terms actually grow faster than root m. So these bounds actually get worse as the sample size goes up, even asymptotically in many cases. So I think we're still very far from understanding the nature and the theory of deep learning. So what this talk is about, with that as context, is how we can begin to overcome some of these problems. And it really is going to be in two different parts here. The first part, and I'll just say while retaining the benefits of deep learning. Now, to be clear, when I say deep learning, I actually want to be very specific what I mean there. When I say deep learning, what I mean is deep learning defined as composable, differentiable architectures trained in an end-to-end fashion. To me, that actually is the crux of deep learning. Deep learning is not about convolutions or ReLUs or particular architectures. It is about the nature of chaining together differentiable modules and training them with a single objective at the end all the way through with backpropagation. That's what deep learning is in my mind. And we want to retain those benefits while starting to, at least, address some of these problems. That's what this talk is going to be about. It's going to be about two parts, really. First, how we address some of the brittleness, and then actually rather separately, how we can address things like opacity and inefficiency, though I should say these are sort of separate ideas right now, and we have not yet really been able to merge all these things. And I think that's a main open question going forward. OK, so that's the outline of the rest of the talk. Let me then jump into, and feel free to ask questions at any point during this. I'll try to still get through most of the material at least. OK, so let's talk first about provably robust deep networks. So here is our adversarial setting. And in the adversarial machine learning setting, instead of trying to minimize our normal, sort of looking at our normal characterization of error or loss, which is sort of the expected value over x, y pairs for classification, or just the loss of this. This could be either like a cross-entropy loss or just the actual error. We move instead to sort of a min-max problem, where for each example, we try to find a perturbation to that example that will actually maximize the loss of the network that the network suffers. And then on the outside, we try to find a single network set of network parameters, theta, that make the network kind of robust to the worst case perturbations here. Okay, so this is kind of the standard min-max formulation. But it's really worth understanding what we're saying here. What we're asking for is the network not just perform well on that first panda there. We're actually asking that it also perform well, i.e. not have that given prediction, when we add any noise inside some allowable region delta. Okay? So delta often, and we will actually take it to be things like the L-infinity norm, though I think a big question going forward is how do we get beyond simple norm bounds like that to more descriptive understanding and semantic meanings for our perturbation regions. So So this is our goal. We want to minimize this bottom thing when we talk about deep learning. And in fact, not just on the training set, that's what I'll mostly talk about here, but we also, of course, want it to be low on the test set. We want a new image to be sort of unable to be perturbed in a way that will change the classifiers too much or increase the loss too much. OK, so why is this hard? Why can't we just do this, right? And the reason why this is so hard in the context of deep networks is the following. So in a deep network, when you take a very nice, even convex region in input space and pass it through the network, what comes out on the other side is some nasty combinatorial non-convex region that's very hard to reason about. And so what that means is we actually can't really solve that inner maximization problem. We can't actually find the worst case point in that perturbation region that maximizes the loss. It's actually ends up being a combinatorial problem to do so. So and that makes it sort of very hard because these networks are huge potentially, and it's very hard to reason combinatorially about things this size. So here's what we're going to do instead. And this is going to be the basis for the first bit of work we did in this area that will also follow up with some of our current work in it. And so our approach at a high level is quite simple. What we're going to do is we're going to form an outer approximation of these the image of these perturbation regions to the network. And we're going to do our robust optimization over these outer convex relaxations. This will be possible because the outer relaxations will be convex. But we're going to do it in a way that lets us easily solve the optimization problem around that outer thing. And what that will do is that will give us really an upper bound on the worst case loss we're going to suffer. And so we know if that worst case loss, or if we don't make an error kind of in the worst case, this outer approximation, we know we're safe in the general case as well. And that's going to be the overall agenda for how we're going to make provably robust classifiers. Of course, how do we go about constructing and then optimizing over that outer region there? So the first part of this idea is actually quite straightforward. The first part is we're going to get this outer approximation by relaxing the nonlinearities in the network. So what, say, a ReLU network looks like in deep learning is a bunch of linear operators followed by nonlinear operators. In that case, the ReLU operator, right? It's the max of 0 and x for each value in the hidden units. So we apply a linear operator like a matrix multiplier or a convolution, and we apply a ReLU. The only part that's hard to capture in an optimization framework is that ReLU. And so what we're going to do is we're going to relax the ReLUs to their convex hull. So suppose we have some upper and lower bound on the value that the pre-activation can take on somewhere in the network. So I'm going to call that L and U here. If we have those things, and don't worry about, I'll talk about how we get those in a second, but if we have those things, we can relax this strict ReLU constraint to instead that triangle on the right there, and say that the pre and post activations only have to lie in this convex relaxation of the ReLU. And if we do that, this is now a set of linear constraints on our pre and post activations. And so what this means is that the problem of finding the worst case perturbation in this outer approximation, that actually becomes just a linear program. Essentially, we're maximizing the last layer of the network in one direction, the direction of the true class. Well, maximizing the direction of a target class, minimizing the direction in the true class, so kind of moving closest towards the decision boundary, subject to the constraint that our first layer has to be within, say, the infinity, some infinity bound of the actual input, and then the constraint that the pre and post activations, instead of actually being a ReLU operator, then instead they have to lie within this convex set. Okay, so that transforms the question there.
Is this sort of applied game theory?
So what we're going to do is we're actually going to solve the inner maximization exactly, and then minimize that whole thing. Now, it relates, of course, to duality in game theory, where you do the same thing. You replace one of the terms you replace the inner term with its dual and just solve one problem, which is actually very analogous to what we do. But I would think of it, because the problem is non-convex, we're talking about upper bounds. I think it's not quite exact. We're not finding an exact equilibrium point, but it's related, yes, absolutely. Okay, so this is great. We now have a polynomial time way of computing these bounds. Because we can also compute, by the way, the upper and lower bounds iteratively, right? We can compute them also with an LP. The only problem here is that to do this, we have to solve a linear program once for each activation in the network, for each example in the network, every time we want to take a single gradient step in our training procedure. And that's, I mean, with the number, by the way, the number of variables in that LP is equal to the number of hidden units in the entire network. This is not exactly a practical algorithm by any means. So to make this practical, we're going to take a few more steps here. And the first one we're going to do is we're going to use duality, and this is actually where sort of the game theory stuff comes back in, to get a looser but much more efficient bound on these problems. So here's the idea. We know from LP duality that every linear program has a dual program, right? And this dual provides a guaranteed bound on the value, the optimal value of the linear program. What we're going to do, and the key insight here, which I'm not going to prove, I'm just going to say this, the details, of course, are in our papers. The key insight here is that if you look at the dual of our linear program, it turns out that this dual is actually identical to the backpropagation network through the original network. So it's basically getting a feasible point of that dual problem essentially involves one backprop pass through the network. Now that actually, to me, I should say that was not at all obvious to me. If it's obvious to you why that's the case, that's fantastic. Please explain it to me. The only way sort of I could figure out how to do it was just going through the actual details of the primal and dual problem and figuring out that the dual was in fact this backprop pass. But again, there may be other ways of doing it as well. Now to be clear, we aren't actually solving the dual problem. That would be just as hard as solving the primal. But what we are doing is we're computing a single feasible solution to the dual, which gives us a guaranteed bound, sort of, as the top figure there sort of shows, an outer bound on the outer bound we already formed, which still gives us these guarantees. So that's going to be our agenda here. And the last thing that I'll say is that to find our upper and lower bounds, we just do this process iteratively using our fast dual solver with some additional tricks rather than just our, solving the LP itself. And so we kind of build these incrementally. We build first the first layer, upper and lower bounds, and we use those to compute the second layer, et cetera. And in the end, we have a process that is only quadratic in the number of hidden units in the network. Now, of course, that's still actually quite high as far as networks go, but I'll talk about in a second how we bring that down even further. Okay, so just maybe taking a step back for a second in case some of this was all a bit in the weeds. In the end, instead of minimizing our normal loss of a network, all we need to do is minimize some other function of the network, which is complicated. It involves these dual problems and solving them with backprop passes, et cetera. But we can implement that once in a framework like PyTorch, and then we're able to just plug that in as a drop-in replacement for our loss, and that gives us a guaranteed upper bound on our actual worst-case robust loss we could suffer under any perturbation. And that's going to be our agenda here. And I should say, because it is a complicated function, I should highlight the fact that the code for all this is available on our group's GitHub page. Now, what does this look like? Well, here's an example of what it looks like. Here's a simple 2D toy problem. If you train a normal network, so here's a bunch of red and blue points. If you train a normal network on it, you get the figure on the left here. If you train a robust network, you get a figure like the one on the right. So it is still going to be a nonlinear function. You don't lose that representational capacity. But what you get is you get a guarantee that no point in that region crosses any of those boxes. So no point actually crosses one of those boxes. And this is, at least when we're doing it, this is some of the first times that was possible for a nonlinear classifier to sort of have provable robustness guarantees on these nonlinear classification problems. Okay, so maybe going a little bit beyond this, at least to one step beyond just pure 2D toy examples would be something like MNIST. We'll get to bigger things in a second. Don't worry. I'm not going to stay with MNIST. But remember, this is quadratic in the number of hidden units. So this naive technique is limited to things like MNIST or maybe CFAR. But let me just show you what this looks like. So if we train a standard deep network, we get great performance, but the error is essentially with an attack, you can basically make it have whatever error you want. If you train a robust linear classifier, so this is actually techniques that have been known since the 70s, how to build this same kind of technology into linear classifiers, you actually do quite a bit better. Linear classifiers aren't awful for MNIST. They're actually OK. But it's still nowhere close to the performance that modern neural networks get. On the other hand, if you use our method, you're able to get a classifier that gets about the same accuracy, in this case, as the deep classifier, so on the level of about 1% error, while we can guarantee that no matter how many papers Alex's group and others write, we will not have our attack broken in the next review cycle, as is common for so many other papers, unfortunately, these days. So we can guarantee that no attack you could ever come up with will have an error higher than 3.7% on the test data for MNIST here. And this, at the time, was by far the strongest balance. But of course, with work that followed on from this, it's been improved a little bit. But this was sort of the first times we had results of this kind for MNIST. Yeah. Yes, sorry, this is an L infinity bound of this epsilon, where the pixels range from 0 to 1. So the 10th of a value of a pixel in L infinity norm. Yeah, great question, sorry. We can also look at how well real attacks perform. So this is sort of a bound on the attacks. And it turns out they actually achieve the bound pretty closely. So for a normal classifier, you can't quite get 100% accuracy, 100% error rate, but you can get like 82 really easily. I think with a little bit of tweaking, you actually could get 100 pretty easily. Whereas our classifier, the bound is pretty tight. So the bound says 3.7% error, but we can actually achieve 2.8% error with real attacks that people actually run on these things. So it's reasonably tight, this range. There's not a lot of room for improvement on these bounds, with the caveat that this applies when you train the network on those bounds. OK, so let me now briefly, with that kind of as context for like the in-depth dive into how one of our methods work, let me briefly talk about some of our ongoing work on how to improve this a little bit. And I think there are really two directions that need to be addressed to do this. The first is that we undeniably need to scale and tighten these bounds. These bounds are loose, at least for networks that are not trained on the bounds. And they also don't scale very well, right? They're quadratic in the number of units, and we need to improve upon that. And secondly, we need to consider perturbation regions that go beyond simple norm bounds. Because when it comes down to it, the images you're actually going to see don't obey some arbitrary kind of norm-bounded similarity, right? If you see a picture from one angle and you see it from a slightly transformed or shifted angle, that's a huge difference in L infinity norm, but it's the same image, right? So we need to move beyond just that for our examples. And so now I'm actually going to go quite quickly here just to highlight some of the work that we've thought about in this space. But by all means, if you have questions, you can ask me about these things afterwards. All these papers are going to be, of course, on my website. So just quickly, we had a paper this last NeurIPS on scaling these bounds using random projections. So the bottleneck of these bounds actually is computing the upper and lower bounds for each activation. This involves essentially taking an entire identity matrix and piping it through the whole network, and then computing row-wise L1 norms along this matrix here. And it turns out you can actually use a Cauchy random matrix, pipe that through, and get an unbiased estimate of the row-wise L with the row-wise L. By taking the median of those things, you can get an unbiased estimate of the L1 norm of the rows. We also extend it to the case of, say, ResNets rather than just normal networks. And the upshot of this is that we're actually able to reduce the runtime from being quadratic to being essentially linear. It's basically a factor of the dimension of your random projection, which we use 50, so 50 times more expensive than training a normal network, which I think maybe we can't handle that, but probably Google can handle that pretty well. Okay? Or at least anything we could do, Google could do 50x without batting an eyelash. Now, the downside to this, though, it still is only scaling to things like CFAR. It's still not quite up to ImageNet-scale. And secondly, the big penalty you pay here is that when you train models in this manner, you pay a big penalty in the clean accuracy of these models. So when you train a robust model, the robustness acts as a very, very strong regularizer on the network, and you don't get nearly the performance you would otherwise. So when you're talking about accuracies in CFAR that are with a perturbation of size 2/255, you get an accuracy of like 31% with a network, and 31% error is horrible for CFAR. And I should even say, you know, this is, and not only are they bad, they aren't even as good as the best empirical robust errors we have. So when you go to more complex problems, there's a big gap between the clean performance we have, the best empirical performance, which is actually the methods that Alexander and others have advocated for of predicted gradient descent training, and then all the way over here are the provably robust errors. So in order to make this practical, we really need to compress this gap a whole lot more in terms of the actual performance of these models. Now, I think we're getting at a different way of achieving this, which I'm only going to highlight briefly, though I'm happy to talk about this more if afterwards people are interested. But we actually are also very recently started looking at an alternative approach for using a very different method based upon randomized smoothing to get guarantees on robustness in our networks. So the idea here is instead of trying to just use our network as it was to classify points, you actually draw random Gaussian noise and classify a bunch of points and take the maximum vote over those Gaussian random samples. And that becomes your new way of classifying an example. You take the majority vote over Gaussian random noise. And the very cool thing here is, somewhat surprisingly, is it turns out that this approach, even though you're talking about classifying random noise here, this approach also gives you a bound on the worst case robustness to adversarial noise. This was, to me, was very surprising, and essentially it involves terms that they increase with the radius that increases with the variance of your noise, and then scales with the inverse CDFs, Gaussian CDFs, of the most likely class minus the second most likely class. Okay? And I don't have time to get too much into the details of why this works, but the basic intuition is that if you think about the decision boundaries that would sort of be maximally bad for this smooth classifier, you can actually prove that using essentially a variant of the Neiman-Pearson lemma from statistics, that the worst case decision boundary for these smooth classifiers are actually linear ones. So you can't do any worse than a linear boundary for these things. And for a linear boundary, you can actually compute what the robustness radius is analytically. So I'm happy to go over that in more detail after the fact if people are interested, but it's sort of this very surprising property and very nice property about Gaussian distributions and L2 distances. And it turns out when you do this, you can get a few things. You can actually get provable guarantees on, because the process here is actually very simple, it's just augment the data with noise and train on that, you can get guarantees against data sets the size of ImageNet, which are actually competitive, not quite competitive. You do still lose accuracy a little bit compared to ImageNet, but you get non-trivial guarantees for ImageNet size data sets. And for the cases that we can compare to our older methods, the ones in green there are our older methods, we actually can kind of improve across them over the board. So to be fair, our older methods are more tuned to L-infinity perturbations than to L2 perturbations, but there's a lot of room to be sort of had there. So we actually improve substantially upon those bounds as well. So that sort of is starting to take care of some of the scaling issues. I think we have a long ways to go still, but we're starting to get a handle on the scaling issues. What I think we need to get a better handle on is the notion of what attacks actually look like. So again, this is back to our sort of adversarial camera sticker that makes stop signs look like guitar picks. In addition to sort of being a nice demonstration, I think this also serves to characterize the fact that these perturbations we're talking about here are actually extremely limited in their scope, right? You can't have high-frequency noise. You're limited to these sort of fuzzy, blurring perturbations of your image. And the question that I think still remains to be seen is, if we limit ourselves to more restricted threat models, can we vastly improve upon the quality of our bounds? We've also done some work on thinking about adversarial perturbations, not just in LP norms, but in norms based upon Wasserstein distance. This required actually a different way of projecting onto the Wasserstein ball. Here we're actually only doing empirical robustness. We can't prove things about this yet. But I think it's another threat model, another noise model that captures better notions of distance in images. So Wasserstein distance in images sort of captures things like rotation and translations very nicely. And I think we want to think about things like this to think about other ways of doing this. So I'm going to give a final thought on this before we move on to the next section, which is from Jeff Hinton here. This is a recent picture, I presume. I would do that, right, if I won a Turing Award. So he sort of says that he used to think that adversarial examples were kind of trivial. Because I think you first see them, and I think you sort of think that, like, oh, this is just an artifact of the digital world. Doesn't really matter. But they are quite fundamental. And I actually agree with this statement. I'm going to disagree with Jeff a little bit later in the talk. But I think that these things are going beyond just sort of exposing a security flaw in algorithms. They're talking about something very fundamental about the nature of the learned boundaries we get from deep learning systems. And in understanding how we can develop systems that are robust to these things, we understand much more about the nature of the actual classifiers we're learning on this data. And so I think this actually is quite fundamental. And if we want to apply these things in real-world scenarios, we're going to have to solve these problems. OK, so I have a much shorter second part now, but I want to highlight another bit of work we're doing, which I think starts to address some of the other problems in our system, namely, or in modern deep learning systems, namely the sort of non-transparency and inefficiency of modern deep learning systems. So to introduce this, I want to sort of give an example here. Oops, that should have appeared there. Hang on one second. Nah, whatever. I'll just do this. OK. So if you think about sort of a traditional, say, control architecture for controlling, say, an autonomous car, the way you would build this is that you would sort of have a controller, have a sensor inputs, you estimate your state, you have a dynamics model, a cost function, planner, et cetera, all the way through to control actions. That's how we design current software. And you would be crazy, what's shown in the bottom here is the same thing, which is a big neural network in the middle. You would be crazy to actually just try to design a self-driving car system that just takes raw sensor data and outputs steering wheel angles and brake. Some people are trying to do it, I know. I think they're kind of crazy. I don't think anyone's seriously doing it and going to put customers in it just yet. What you instead do is, of course, you use actual modular programming, right? This is everything we've learned about programming says build modular programs that each address a certain task of this. They have well-defined inputs and outputs. And we're throwing a lot of this out when we think about deep learning. So what I want to argue here is that we can actually get a lot of the benefits of the top section while still remaining in the regime of deep learning. And the way we're going to do this is we're going to think about what these modules contain. And what a lot of them contain are things like the solution to optimization problems. So we take an optimization problem and we solve it. And the output of, say, a controller is the solution of an optimization problem that was specified by its inputs. And it turns out you can actually embed optimization problems very easily in deep networks. So one approach we sort of have really pushed for is embedding things like quadratic programs not as sort of ways to solve networks, but themselves as layers in neural networks. These things are much more expressive than traditional layers, and they can capture a sense of direction and intentionality in what we want the layer to do. It's very difficult to do otherwise with, say, a linear operator. So the question, of course, is, how do you do this? Well, the question what that really boils down to is how do you compute backprop through an optimization problem? And that's actually the problem that we solve, or we show how to address in some of our work here. So again, a little bit in the weeds now, but we can pop back up in a second. The way you do this is that you look at what makes a solution optimal. Well, it obeys certain fixed point conditions. For an optimization problem, these are known as the KKT conditions. That's what makes a fixed point optimal for an optimization problem. You can easily, actually, though, apply the implicit function theorem to basically differentiate this. So we're going to get a bunch of terms there that involve either differentials of the variables of the QP itself. That sort of involves like the inputs to the QP. or involves differentials according to their solution. And all you really are doing here is that this actually ends up being a set of linear equations in the unknowns, which are the unknown derivatives of our solution, and the known things, which are the derivatives of the known quantities in the QP. And so it turns out that solving the derivative of a QP, differentiating through a quadratic program, just involves solving a single linear system at the solution to that quadratic program. And so this means actually a couple of very cool things. Now, you have to do a few special things to make this to work well. So optimization, is relatively slow compared to sort of forward passes. So a lot of the work we've done in this area has actually been about building very fast custom solvers using GPU acceleration to solve many QPs in a batch setting. But the very nice property here that you actually get for quadratic programs is the following. So that linear system you have to solve at the end of the quadratic program is actually, to get backprop through it, actually ends up being the exact same linear system you solve in the last iteration, say, of an interior point method to solve that QP in the first place. What that means is, if you solve the QP exactly using, say, an interior point method, you get backprop for free. So backprop costs you nothing once you've solved the QP to begin with. So every solver can easily be made differentiable. Every solver of a certain type can be easily made differentiable because it's no extra work. And that's a very, very nice property. And again, of course, we have all this open source on our lab page. Just to give you an illustration of what this kind of looks like, I'll give two quick examples of this and then move on to sort of more realistic applications. Here's a simple example of learning constraints in a polytope. So we're actually learning, we're assuming our points are generated by the solution of some QP, and we're assuming that, and we want to learn what's the constraint set that generated those solutions. And by just gradient methods, kind of amazingly, we're able to actually learn the set of constraints and objectives that actually led to those input-output pairs. And when you actually cannot, and in most cases it fits it exactly. In other cases, when, like the one on the bottom left here, when there aren't enough points in your solution, it comes up with a pretty good approximation. So it seems like these sort of gradient-based techniques to learn the constraints of an optimization problem wind up doing a pretty good job through these differentiable programs. So to be clear, differentiable layers that solve optimization problems. Another fun thing you can do is actually learn to play games like Sudoku. So we actually learn to play the game of Sudoku from examples. Now, to be clear, this is not a good way to actually solve Sudoku problems. You should not do it this way. It's a really simple search problem. What's cool here is that we are showing that this is actually a pretty hard problem for most networks. It involves global constraints across the output space that are very hard to satisfy for things like convnets. And what we show, and actually this is just the problem here, we basically think about a generic kind of smooth version of the Sudoku problem, where the P input to the system is a one-hot encoding of the unsolved puzzle, but the actual LP, or the actual constraints themselves are completely left up to random, initialized to be random and then figured out by the algorithm. And after a few epochs, we're actually able to very accurately essentially encode the rules of the game Sudoku just from learning examples, just from seeing examples of unsolved and solved puzzles together. And potentially the sort of baseline is even for the Mini-Sudoku, which is a 2x2 game, a 4x4 game, the best COMNet we have achieves about 6% error, whereas OptNet essentially it learns it. It just is able to learn the actual constraints and can solve it exactly on the test set. Okay, so let me just mention two more applications here, one a little bit longer than the next, that are sort of following the same tradition before I end with some final thoughts. Yeah, question?
Why does the error oscillate?
Yeah, that's a good question. Why does the error oscillate? So we're minimizing a squared error in our solution and in the one-hot encoding of our solution versus the other thing. And because this is a relaxation of the original problem, we oftentimes don't get an exact solution, and so there is some oscillation between trying to fine-tune this sort of L2 loss in a way that actually guarantees that you're going to be exact. That causes some oscillation. We actually can fix that by a little bit of better smoothing and outer optimization, though that, I think, is one of the key problems. The outer optimization is actually, for more complex things, one of the key problems, so I don't want to sweep it in the way entirely, and I'll mention that again a little bit later. Yeah? The QP? Yeah. Yeah, so it's solving a QP is cubic in the size of in the size of it. So it ends up being cubic. Yeah, polynomial. Oh yeah, so that's a great question. So Sudoku actually is, in fact, not solvable by a QP. You have to work really, really hard to find a Sudoku problem that cannot be solved by its LP relaxation. And so we just assume that for the size we care about, we're approximately solving it. And if not, actually, this sort of learns a good relaxation to solve it. Yeah. OK, so very quickly, we've used similar techniques in the context of learning games. So if you observe two players playing a zero-sum game, you actually can assume they're playing according to some sort of soft equilibrium and embed an actual equilibrium solver within a network to figure out what are the costs these two players are playing according to. And we're actually able to learn things like security games. Even for extensive forum games, we're actually able to learn not just the policies people are following, but the actual underlying payoffs that led to those policies. As a final note, actually in collaboration with some people here, we've done the same thing for physics engines. So physics, actually rigid body physics, can be expressed as a linear complementarity program that encodes things like joint constraints, which are quality constraints, contacts, which are complementarity constraints, and friction, which is another complementarity constraint. And it all leads to a big set of equality constraints along with inequality constraints and these things called complementarity constraints, which means that the product of two vectors is equal to 0. Those things can be differentiated in the exact same way, and you actually get a very similar way of differentiating through optimization or through dynamics. There are other ways of doing this as well, but this sort of fits very easily into our framework of differentiating exactly through fixed points. And so when you do this, you can do things like embed physics engines within encoder-decoder architectures. So what we do here is we actually learn an encoder of these sort of 3 billiard balls bouncing around, try to then simulate forward what happens, and then predict what's going to happen in the future. And by ensuring that this simulation obeys the laws of physics, we're able to make very long-term rollouts and predictions that don't kind of blow up. They actually maintain kind of making predictions that evolve according to the laws of physics because we've constrained the underlying state representation to actually obey the laws of physics. Maybe even more so, we've also actually learned to do model-based RL on games like Atari using these constraints. So here we actually hook up several different things. So we hook up our sensor inputs, in this case the pixel values, to an image segmentation engine, which actually that part is hard-coded, but the rest is all learned, to a rigid body dynamics method, to LQR solver. And if you do this all together, you're able to learn the game of how to play Breakout in Atari. The nice thing about this, though, the very cool thing about this, which gets to the final point I made about the efficiency of solvers, is that you're able to do this in about 1,000 samples of data. So after about 1,000 samples of data, we can almost, not quite, because there's a little bit of a gap there, but we can almost approach the performance that deep Q learning achieves after 10 million samples from data. So when you embed this structure into problems, you do get this advantage of being able to understand and learn your system from much sparser amounts of data, precisely because you've encoded the structure of the problem into it. One thing you can also do, and this gets back to the final point I made about debugging systems, is you can look now internally at the predictions the model makes. I mean, you know what the role of your physics engine is in that differentiable end-to-end framework. You can look at its predictions, and so if you mess up there and don't hit the ball, you can see what the physics engine was doing underneath it, and ideally then come up with a plan to diagnose what the issue was. Right? And that's a very different way of debugging and diagnosing problems in machine learning than what we currently do with most deep learning architectures. So as a parting thought for this section, again, bringing up Jeff Hinton, he says that he has this sort of famous quote saying that neural networks get all their structure from data, not from people putting little programs inside them. And here I actually strongly disagree with Jeff. I think Rich Sutton actually wrote a similar argument recently, a few weeks ago. And I vehemently disagree here, because I would actually argue that the success of deep learning is precisely by people putting little programs inside of them. I mean, convolutions are a little program. Transformers, self-attention, that's a little program. And deep neural networks without those things, they don't work. They only work as a function of people putting not much structure, but a little bit of structure into them. And I think we can actually play this game in a much more fine-grained manner, where we're starting to put more and more structure into these things, enabling more and more sort of intentional, understood behavior that becomes more and more efficient. And by doing so, we can actually greatly benefit the entirety of this field of deep learning. So I have only a few sort of last thoughts for the path forward. These are sort of more notes for me. Rather than end just by summarizing everything that we did here, I have one slide with all the things that we did at the end, or at least some of the things we did at the end. What I want to actually highlight is if I were to be asked what my biggest questions were, I want to give a few instances of what my biggest questions are in these areas. So where do I think there's the most progress to be made, or what sort of keeps me up at night when I think about what will prevent our systems from being non-brittle, transparent, and efficient? So my biggest question when it comes to adversarial robustness is essentially there does seem to be a fundamental trade-off that we saw between robustness on the one hand and kind of clean standard performance on the other. And so as we get more robust, the big danger, and actually there's been a lot of work by people here in the room on these same topics. So there's this danger that as we improve robustness of models, we will lose the benefit of a lot of our deep learning systems. And that may be an actual thing. There may be an unavoidable trade-off there. However, I don't think we've even begun to scratch the surface of really exploring that trade-off yet. I think we don't know the classes of models. We don't know the optimization procedures. We don't know sort of the architectures that are best for robustness, because we've spent all our time so far optimizing for clean accuracy at a meta level, right? With graduate student descent, that's what you guys have been, and we've all been working on. So can we much better understand what's the actual sort of Pareto frontier of robustness and clean accuracy, not just a few sample points on it? And secondly, how on earth are we going to actually express the space of semantically equivalent perturbations? If you look at me here, and you see an image of me here, you know that's me. Even if I blurred out some pixels or put a little toaster up in the corner. Now, if you put that same number of pixels that are being changed up here, and you put it over my face, you would not know who I am anymore. So somehow our perturbations that we think we should be robust to encode semantic meaning. This is now a chicken and egg problem, because how do you encode semantic meaning? Well, you use a deep network to do that, but that deep network itself has problems. So how do you get at starting to encode real semantic equivalence in the context of adversarial perturbations? I don't know yet. When it comes to structured modules, I think including structured modules in the loop of things, I think, of course, there's the question of what more can we do, right? We've had a string of papers now doing the same idea on different domains. We've gotten a lot of good mileage out of it, but there are certainly more to be had. But the bigger question I have is this. When you introduce these more structured, complex models into these larger differential and frameworks, pure gradient methods to train them no longer seem sufficient in many cases. So you get stuck, all of a sudden all the local optima that we no longer worry about, apparently, in machine learning, come roaring back. And you oftentimes, unless you initialize well, you cannot construct good parameters for your problem, for your complex module that actually work well. So how do you actually go about doing that in a way? How can we think about different higher level search procedures that actually are able to give us the benefit of these complex end-to-end systems while still using first order or, in fact, beyond first order methods for learning? So with that being said, I want to just finally mention that all, of course, the papers and the code are available on my website and the links therein. It has been really wonderful being here, and the sessions I had today have been fantastic. It is always great, as Alex says, to be back. And thank you very much for coming.
We have a time for one, maybe two questions to Zico.
Yeah.
So there is this group at Institute for Advanced
Okay? Mm-hmm.
And they're using sort of associative learning and coupling
Yeah.
and doing things agonistically.
Right.
How does that fit into your program?
Yeah, so in the 80s, right, there was a plethora of methods to train networks. It wasn't like everyone just worried about backprop. There was a million methods, and there was hot field nets and the kind of stuff that you train very differently. That has now all fallen away in favor of first order methods, SGD on everything. Learn everything by SGD. I don't know if associative methods are the right way of learning things, but I think we do need to move beyond just do everything with SGD, because there are these real cases where it gets stuck, we can't make progress, and when you build architectures that you want to build, you can't do that, and you can't train them with SGD alone. So I don't know if associative learning is the right strategy, but I think thinking along those lines is a direction that is necessary for the future of deep learning.
One more question.
Yeah.
So I haven't read the most recent work that you talked about, but from your earlier work on, for example, playing Sudoku,
Yeah.
I remember saying that you didn't, you were training in a more supervised setting.
Oh, we're training it in a supervised way entirely, yes.
Yeah, but where I would like this type of work to go is where your supervision is much more direct. So you can imagine
Right.
you have some sort of inference module, and then you have all sorts of computation on top of that.
Right.
They have binary labels.
Yeah.
How can we possibly train this?
That's a great question. So I think ultimately you are going to be limited a little bit by the signal you have available. So if you have a single, again, maybe by backprop, right? If your paradigm is backprop for everything, it might be ultimately limited because the backpropagation signal you get through your whole network from a single binary label might just be too weak to really learn. Now, this actually relates, I didn't talk about this too much, but we do have sort of a framework we thought about a lot based upon task-based losses using the system. So the idea is, when we use predictions in a machine learning model, that's not kind of the end goal, right? A prediction is not the end goal. The prediction is a part in a much larger closed-loop system where we actually use the prediction to do something else, take some action, then suffer some loss based upon that action. And so the cool thing about these frameworks is we can start to encode kind of more and more of that closed-loop process into the actual differentiable architecture such that we can actually backprop through the whole thing based upon that single binary signal at the end. Whether or not it's enough is to be seen, but you at least can take your whole architecture as not just a predictive model anymore, but the predictive model, the decision maker that uses that prediction, and then the task-based very complex loss that will result from that under your sort of hypothesized setting here. So that, I think, is a much more direct way of kind of doing data science, I guess, in a deep learning setting, where you actually encode the entire pipeline as your model and train based upon that. And with these methods of sort of differentiating through everything, you can at least do first order approaches for that. But whether that's sufficient, I think it definitely is not. So we need to think about how to make that more sufficient.